All right, the divides relation. So we know what division is, and this is just basically creating an operator for division. So we use the notation A with a line B to denote A divides B. Okay, so when we say A divides B, that means that B can be divided by A evenly. There's no remainder. So a formal definition, if we have A divides B, that means that we can write B as A times some integer k. All right, so it's pretty easy to figure this out with smaller numbers. So we'll look at an example. So determine if A divides B. All right, so first we have 4 divides 20. Secondly, we have 20 divides 4. So if we look at 4 divides 20, that would mean that 20 can be written as 4 times k. And that's true, right? There's k equals 5 works for that. And so this would be a true statement. 4 does divide 20. Secondly, if 20 divides 4, that means that we can write 4 as 20 times an integer. And there's no k that makes that work. So in this case, we would write 20 does not divide 4. So we'll still use that same line. But we'll cross it out. All right, so let's look at another claim. So let A, B, and C be integers. So if A divides B and B divides C, then A divides C. That's our theorem, our claim here. So we're just going to go ahead and prove this right away. So we're going to assume that A divides B and that B divides C. So what does it mean if A divides B? By definition, it means that B can be written as AK for some integer k. Similarly, what does it mean if B divides C? C is equal to B times some integer L. And so our goal is to show that A divides C, which means that C can be written as A times an integer, A times P, we'll say. So we already know that C is BL, but B is really A times K. And now we can change around these parentheses by associativity. And so we wrote C is equal to A times some integer. We'll call it P. So therefore A divides C, and we'll put our tombstone.